All right, these are solutions for evidence 1.1b. I want to start off with a little review of significant figures. If you were to ask me how much I have in my bank, and I told you that I had $3,000, I think it would be foolish to say that I had exactly $3,000, because that response is a little bit ambiguous. You see, whether I had $2,900 or $3,150, I might answer that I have $3,000 in the bank. And that's true, I have about $3,000 in the bank. But if you asked me how much I had in the bank and I said, I have $3,000.15, then I think that answer is a lot different. You see, the fact that I have specified out to the number of pennies what I have in the bank lets you know that probably all of the digits that I gave you are meaningful and significant. Let's review significant figures just briefly before we get started. So, in practice 1.1b, notes 1.1b, I gave you some rules. There's 4 rules for determining the number of significant figures in a value. The first example that I have here is 304,000. Rule number 1 says the leftmost non-zero digit. So the leftmost non-zero is significant. Rule 2, the rightmost non-zero is significant. That would be the 4 in this case. Rule number 3, the rightmost trailing zero, that's this one, is only significant if it occurs after a decimal point, which is not true in this case. So this is not a significant digit. And the 4th rule says all digits sandwiched between significant figures or significant digits are also significant. So that would include this little 0 in the middle. You see, this number has 3 sig figs. Next, I have the same number written in scientific notation. You see, this is 3.04 times 10 to the 5th. That's the same as 304,000. And truthfully, the same is true. You see, this 10 to the 5th is just a way of marking off place values. It just tells us where our decimal point is, but it doesn't affect the number of significant figures at all. So the same as before, we run through our little list of leftmost non-zero, the rightmost non-zero, any number in between. There are no trailing zeros after the decimal, and again, we have 3 sig figs. Next, we have the number 304,000.0. First, the leftmost non-zero number is significant. The rightmost non-zero number is significant. The rightmost trailing zero, that would be this one, is significant if it occurs after a decimal point, which in this case it does. And finally, all digits sandwiched between are significant. So in this case, we have 7 sig figs. And finally, I have the number 0.001050. Let's roll through one last time. The rules: the leftmost non-zero number, so in that case this is the 1. The rightmost non-zero, that's the 5. The rightmost trailing zero, that's this 0 here, it is significant if it's after a decimal, which in this case it is. And then any digit sandwiched between. So as you can see here, I have 4 sig figs. All right, it's important that you understand these rules and are able to quickly not only identify the number of significant figures in a value, but also identify where to round in order to have a certain number of significant figures. All right, let's step into the evidence. I'm going to roll through. First of all, I'd like to say that a number of people made notes on their work that was really helpful in figuring out what things people had questions with. And actually this video is a response to about 6 or 7 students that wrote me notes or had questions or emailed me about the evidence. And so if you do have questions about work that we do, make sure that you're doing that you're emailing me, that you're keeping in touch either through email or writing notes to me on your papers, because I take those things very seriously. All right. Number 1, which of the following shows this number rounded to 3 significant figures? Well, we have to kind of have an idea of how to get that number to 3 significant figures. And we kind of have to know that these 2 zeros are never going to count for significant figures. And so 3 significant figures would really be those 3 there. You see, if I rounded the value off after that, I would have 3 significant figures. Now, we use this 8 in order to determine that rather than rounding down to 0.0805, we are going to, since this is 5 or more, right, we're going to round up to 0.0806. And so this is the value we're looking for, right? So let's see. Number 2. We have a multiplication problem, and we could just type this into our calculator and get an answer that was like 25.234. You see, but this answer has too many significant figures, and the proper number of significant figures would be the least number of significant figures between these 2 values. Well, both of them have 3 significant figures. This 0 is after the decimal point, so both of these have 3 sig figs. So we would want our answer to have 3 sig figs, and that would be here and here and here. I need to round off at this place, and so we need 25.2. We would round down in this case. Since this 3 is 4 or less, we would round down to 25.2. We have meters times meters, right? Meters squared. All right, so we have 25.2 meters squared. Next up, which of the following numbers has the largest number of significant figures? Well, in this case, we would run through our rules, right? The leftmost non-zero, the rightmost non-zero is the same thing. Is this 0 after a decimal place? No. So this has 1 sig fig. Same thing here, 10 kilograms has 1 sig fig. You might ask about the tera or the kilo, but those really are like saying the kilo is like saying 10 times 10 to the 3rd grams, right? Because this is what kilo means, is times 10 to the 3rd. And just like before, we do not include those in our decision-making process for significant figures. Those are just place values. All right. Moving on, 11 has 2 sig figs, and 10.0, this is our leftmost. That's also our rightmost non-zero. We have a 0 that's trailing behind a decimal, and we have sandwiched significant figures. So this has 3 significant figures, and that means that it is the number with the largest number of significant figures. All right, moving on. Number 4. Four says this. It says 4.15 times 10 to the 6 newtons times 9.48 times 10 to the negative 4 meters. See, we have 1, 2, 3 significant figures here, 1, 2, 3 significant figures here. Our answer needs to have 3 significant figures. So we put the whole thing into our calculator, just as it is. If you have questions about how to type in times 10 to the 6 or times 10 to the negative 4 into your calculator, I put some directions on how to do that with your calculator in the notes for 1.1b. When we do that, we get a number like this. We get 3,934.2. In order to have 3 sig figs, we want to round this number off. Right? 1, 2, 3 sig figs. We want to round this number off here. And so, is it closer to 3,930 or 3,940? And the answer is 3,930. So we would round down to 3,930. We have newtons times meters. That's a newton meter. All right. number 5. So number 5 looks more difficult, but really it's the same thing. We are going to identify which of these 3 numbers has the least number of sig figs. This number has 1, 2, 3, 4, and this one counts as well, 5. Here, the same thing. This one counts. This one, 1, 2, 3, 4, 5. Here we have this 0 does not count. So run through our rules. 4 sig figs is the least number. These both have 5 sig figs. So we want our answer to have 4 sig figs. We put the problem into our calculator just like it's shown. We include all of the digits when we're calculating, and the number that I get when I put that into my calculator is 99.55443,003. It just keeps going. Maybe on your calculator you might have even more digits, but the real thing is that we want to have 4 significant figures in our answer. I had some people tell me that in science you always round to 2 digits after the decimal point. And I think that that is what you had been taught up until this point, but the truth is that the correct way to represent answers is more sophisticated than that. And so for younger students, we still don't want them to write out the full answer, but we don't give them the truth. We don't give them the truth. We give them a simplified version of the truth. So, and now we're in DP physics, and we give you the real truth that we need 4 significant figures here. We would round down because of this next digit is a 4, and we should represent our answer as 99.55. We have meters times meters times meters. That's cubic meters. All right. Next up. Same story. We have 3 significant figures here, 3 significant figures here. Now we are not multiplying, we are dividing. But when we put this into our calculator, we're going to want to have, since they both have 3 sig figs, the least number of sig figs is 3. We're going to put this into our calculator, divide. We get a number, something along the lines of it's huge, right? You certainly wouldn't write that whole value out. We want to round to 3 significant figures, which will be those 3. We're going to round down because of the next digit and represent our answer as 35.5. We have units of meters per second divided by seconds, which is the same thing as meters per second times the reciprocal of seconds. And so we're going to get meters on the top and seconds times seconds on the bottom, or as IB would like to write this, meters per second squared. That would be the units. Just point out. All right, number 7. In number 7, rather than writing out scientific notation, we are given some metric prefixes. We have a table that shows us what those values are. So let's rewrite this. Instead of the metric prefixes, let's put in the exponents. So we have 5.00 times 10 to the what? Tera, capital T tera, stands for 10 to the 12th. And so we have times 10 to the 12th. That is what tera means. So now we just have meters times 25.0 mega. Mega stands for, this is available in your data booklet on page 2. It's always available to you during every evidence if you have your data booklet that's unmarked, as well as it's in the notes for 1.1b. Mega stands for 10 to the 6th. So we have times 10 to the 6th, that's what mega means, meters. And both of these numbers have 3 sig figs, right? 5.00, those are both significant. It's much different than saying just 5 to say 5.00, right? You're being more specific than that. And 25.0, 3 sig figs. We're going to multiply those two and represent with 3 significant figures our answer. If you put those this into your calculator correctly, you should have 1.25 times 10 to the 20th. So your calculator might say something like 1.25 times 10 to the 20th. And the units are going to be meters times meters, meters squared. Right? So we're talking here. Number 8. Here we have some more metric prefixes. Micro, that's 10 to the negative 6. So it's the same as 2.41 times 10 to the negative 6 meters times femto, that's 10 to the negative 15. Put this into our calculator. Preliminary 1, 2, 3 sig figs. Oop, that doesn't count as a sig fig. 1, 2, 3 sig figs, right? So our answer should have 3 significant figures in it. When you calculate this, you're going to get something like this times 10 to the negative 21 meters squared. Interesting point here. This square meters has nothing to do with this exponent here. You see, we're not going to square this number or anything along those lines. What this square meters represents is just the idea that this is 1.96415 times 10 to the negative 21 meters times meters, right? Okay. So, so these two exponents are quite different. This only has to do with units, and this has to do with a place value, right? It's really like 0.000. This is a very, very small number, right? 0.00000, 20 zeros, and then 1.96415, all right. So we have number 9. Kilo is times 10 to the 3rd. Micro is times 10 to the negative 6, so we could represent this 3.6 times 10 to the 3rd meters times, oh, that's goofy, 5.2 times 10 to the negative 6 meters. That's just, you know, again, saying that this is what kilo stands for. This is what micro stands for. All right. This, I don't know if we've gone over this or not, but this letter right here is not actually one of the Arabic numbers or letters. It's mu. It's pronounced mu. It's a Greek symbol. I should write it out because a lot of people they write it like an M, but the truth is, like, if you look back at your elementary school work where you had those, you would write in between these lines like this. Like if you were going to write a capital A, you would write it, you know, like this sort of thing, like in elementary. And this would be like how you'd write a lowercase a, or how I would, probably not how you would. But a mu actually looks a lot like a cursive U, but it starts below the line. This is mu right here. And in physics, it's the prefix that we put in front of SI units when we want to represent times 10 to the negative 6. All right. So we have, back to our problem, sorry. We have 3.6 times 10 to the 3rd times divided by 5.2 times 10 to the negative 6. We're going to end up with 6.5 times 10 to the 8. You know, this is a mistake actually, but I'm just catching it now. That would have no units on it. You see, you know, if we had meters divided by meters, both of those would cancel out. There'd be no units on that. Like, terrible having a mistake on my test. Sorry about that. All right, finally, we're converting 55.4 grams into standard SI units. Well, grams is a measure of mass, but it's not the standard SI unit for mass. This is a little tricky. There's a prefix in the standard SI unit for mass. It's kind of weirdo, isn't it? So in mass, if we want to measure mass, we actually measure not in the gram, we measure in the kilogram in SI units. So we need to say, all right, we want to get that many grams converted into kilograms, and in order to do that, we need a relationship. And so let's write out, what does a kilogram mean? 1 kilogram is equal to, well, what does kilo mean? Look it up in the table. It says kilo is equal to times 10 to the third. So I could replace kilo with times 10 to the third. All right, so 1 times 10 to the third grams. And we're going to use this equality here to make a fraction in order to convert. And so we could make two fractions out of this. One looks like this, 1 kilogram over 1 times 10 to the third grams. That's equal to 1. Or we could also write 1 times 10 to the third grams over 1 kilogram. That's also equal to 1. Either one of these two fractions will work. They're just... All right. So let's work on our problem here. We have 55.4 grams. We want to convert by multiplying by one of these factors. When we multiply fractions, I'm going to make that a fraction by putting it over 1. In order to cancel grams and get into kilograms, I want to cancel this gram in the numerator. I'm going to need a gram in the denominator. That's what tells me which of these two fractions I want to use. It's this one right here that has a gram in the denominator. I'm going to write 1 times 10 to the third grams is the same thing as 1 kilogram. You see, by multiplying this value by 1, I'm not changing it. And so I have this gram is going to cancel with this gram. And all my units that I'll have left are just kilograms. So I have 55 point, and I just multiply across, right, to find the new numerator. 55.4 times 1 is 55.4. I have kilograms up here. 1 times 10 to the positive third is 1,000. I have to divide my numerator by my denominator. I get 0.0554, and my units are kilograms. So 55.4 grams is equal to 0.0554 kilograms. Rock on.